Hello. In this lesson, we're going to kind of take things easy and introduce ourselves into Chapter 10, talking about power calculations, by just focusing on the fundamentals. We're going to talk about how to calculate power using our steady-state sinusoids, but specifically we're going to talk about two things. Average power, or real power, which is measured in watts, and a thing called reactive power, which is, you can think of it as that complex imaginary component of power, which is measured in a new unit called volt-amp. Volt-amp reactive, or VARS. Sorry, I couldn't remember what the R stood for there for just a second. Yeah, so a new unit called VARS. We'll go through, we'll see what the formulas are for each of those things, and we'll work a couple simple examples to calculate power, and then we'll send you on your way. So let's get right into it. Power calculations start exactly the same way they did in your Circuits 1 class, where power is equal to volts times amps. That's given in watts, or W for short. The thing is, here now we're in our time domain. We've got our time domain sinusoid, so our P is now a function of time, V is a function of time, and I is a function of time. And we remember from the previous chapter that our voltage is equal to Vm times the cosine of omega t plus, we'll call theta v, and that's the power, and our I is equal to I sub m times the cosine of omega t plus, let's call this theta sub I, and that's given in watts. Now we can distill this down to not a more simple equation. This is pretty simple, but we want to get into a form, and we'll see why here in just a second. But some crazy algebra is going to happen, and we're going to jump straight to the punchline, which is that power is equal to this sort of long, monstrous expression. Vm times Im over 2 times the cosine of theta v minus theta I. So the phase angle of the voltage and the phase angle of the current, plus Vm Im over 2 times cosine theta v minus theta I. So the exact same thing there, but this time it's times the cosine of 2 omega t, and then it's minus Vm Im over 2 times the sine of theta v minus theta I times the sine of 2 omega t. Now, this is a long, gross expression, but we can simplify it and pull out some components that are pretty important to what we are doing. So the first thing we would notice is that we've got this component right here appears again just like that. And that's what we're going to call the average power. You can also think of it as the real power. This is the stuff that dissipates as heat out of our components. And we're going to denote it with a big capital P. And we'll write that again, that Vm times Im over 2 times the cosine of theta v minus theta I. Now its counterpart is this guy right here, the Vm Im times this, or 2 times the sine of theta v minus theta I. This is what's called, ooh, by the way, we need to make a note that this is given, average power is given in watts. That'll matter here in just a second. That other component with the sine is called the reactive power. You can sort of think of it as the imaginary component of power. We're going to denote it as, not look too much like a theta, capital Q, and that's equal to Vm Im over 2 times the sine of theta v minus theta I. Now this is given in a unit called volt amp reactives, or VARS for short. So power systems guys use VARS and talk about VARS and messing with VARS all the time. So if you become a power systems engineer, VARS is going to become your jam. So let's see. So that's average power. That's reactive power. There's one more sort of thing that we'll talk about right now, and then it'll come up again later, but it's called the power factor. And it basically just tells us which comes first, the voltage or the current. We'll denote it as little p, little f, and it's equal to just cosine of theta v minus theta I. And you'll sometimes refer to this, you'll hear people say, leading power factor or lagging power factor. We'll talk about what those guys mean in an upcoming lecture. But there we go. That's how we calculate power factor. It's just this bit, the cosine of theta v minus theta I. There's also, by the way, a reactive factor, which is equal to, you guessed it, the sine of theta v minus theta I. But it's much, much less commonly used than power factor. But it does exist, and it is a thing. And now before we call it a quits and work on an example, I want to quickly make a note of the RMS values as they pertain to these power calculations. Remember that our VRMS is just equal to the VM over 2, and the IRMS is equal to the magnitude, or the maximum amplitude of the current, I sub m, over, not 2, but square root of 2. Square root of 2. So if we go back and we notice the average power up here, we notice that it's Vm times Im over 2. So we could say that Vm times Im over 2 is equal to Vm over the square root of 2 times I sub m over the square root of 2, right? Or we could just say V RMS times the I RMS. So if we want to go and write a slightly more simplified form of our average and reactive power, we would say that P is equal to V RMS times I RMS times the cosine of theta V minus theta I in watts, and that Q is equal to V RMS times I RMS times the sine of theta V over theta I. And don't forget that's given in this new unit, VARS. If I could write it not terribly, VAR. There we go. Okay, and that's all we need to know about power calculations. So let's jump into a couple of examples. All right, so for those of you following along in the textbook, this is from example 10.1. And what it does is it gives us two terminals sort of feeding into a sort of mystery box, and we don't know what's going on the inside of the box, but we do know that there's a voltage V on the terminals and there's a current I on the terminals. And we know that the value of V of t is equal to 100 times the cosine of omega t plus 15 degrees in volts, and that I of t is equal to 4 times the sine of omega t minus 15 degrees in amps. So then we want to find a couple things. Part A wants us to find, or actually we'll just kind of combine these all as one. We're going to calculate the average power, like we just talked about, and we want to know if it's delivering or absorbing that power. And we want to calculate the reactive power. And also know if it's delivering or absorbing. So let's do the average power first. So we know that our equation for P is given as just V RMS times I RMS times the cosine of theta V minus theta I. There's one minor calculation that we have to do before we can just drop it in here, and that is because we have to notice that we have sine here. So we're going to rewrite our I of t as 4 times the cosine of omega t minus 15 degrees minus 90 degrees. So that I of t is equal to the 4 times the cosine of omega t minus 105 degrees. So what we'll do now is take these and plug them into our value. We'll have that p is equal to, VRMS times IRMS. We'll write it in that sort of original way that we were given it, 100 times 4 over 2. Now it's times the cosine of theta sub I, which was theta sub v, which is 15. So cosine of 15 degrees minus negative 105 degrees. A little bit of quick simplification before we get our final answer. 100 times 4 divided by 2 is just going to be equal to 200 times the cosine of 15 minus negative 105 is 120 degrees. So from there, we find that our power is equal to minus 100 watts. And since it's negative, the power dissipated is negative, we know that it's delivering that average power. So, same deal for our reactive power. Q, remember Q is equal to VRMS times I RMS times the cosine of theta V minus theta I. We'll go ahead and jump to the sort of end point here. We'll say that Q is just equal to 200. Oh, I messed that up. It's not cosine. It's IMS times the sine of theta V over theta I. So it's 200 times the sine of 120 degrees. And that's just equal to a final answer. Q is equal to 173.2 VARS. And since it's positive, we know that it's absorbing those VARs. And there we go. We have a pretty simple equation. All we got to do is drop our values in, get our answers, and there's how we calculate average power and reactive power. Okay, this one final example that we want to do for this section is pretty simple. The statement just says a sinusoid with Vm equal to 625 volts is applied to a 50 ohm resistor. So what is our power P? So when we're given basically just this, we can distill it down, especially since it's just through a resistor. There is no active component, or no reactive component, I should say. It's all real. We can use our sort of basic equations that we've already talked about. Remember, P is equal to V RMS squared over R. By that same token, it's also equal to P is equal to I RMS squared times R. And since we're given V, we'll just go ahead and plug it in. P is equal to our V RMS, so that's going to be 625 over the square root of 2 squared over 50 ohms. And nothing to it, punch that into your calculator, and you'll get that P is equal to 3,906 watts. And there we go. So if you're given just a resistor, if there's no reactive elements to that circuit, you can use these really simple equations to solve for power. And that's all there is to it. All right. Well, hopefully that was pretty easy. Just to recap, we talked about two main types of power. We talked about average or real power. We talked about reactive power. You can think of it as that imaginary complex component of power. We talked about how the RMS values of V and I fit into those equations. We talked about if we only have a resistive load, then those power calculations are super easy. P is equal to V RMS squared over R, or P is equal to I RMS squared times R. We worked a couple simple examples, and I think that is it for this lesson. So, as always, if you have any questions, comments, or concerns, please let me know, and if not, I'll see you guys in the next lesson. Thank you.